I certainly can, so it sounds like it's working. So good morning. Welcome to. It's a privilege to be the first speaker at SSPD, and I'm going to take you on a bit of a journey. As none of us are doing any travel at the moment, I thought I'd take you on a bit of a Middle Eastern themed journey through the defense signal processing project that is Stone Souk. So you'll discover why it's themed in a minute. If you wouldn't mind, please.
Paul, your audio is dropping out a little. I don't know if you can move your microphone closer to your mouth.
Yeah, I can do that. If that doesn't work, then I might have to come up with another option.
You could always, if worst case scenario, you could always switch off your video to get more bandwidth.
Seen enough of my pretty face. Okay, so if this was a paper, there would be a large number of co-authors, and I've tried to mention some of the key authors in the acknowledgement thing at the bottom. This is an open source project, so there are more contributors to this than one could possibly name in the time allowed. So you'll see that I try and acknowledge some of the contributions as we go through. But what I'm going to try to do with this paper is to talk to you a little bit about an open source project for tracking and state estimation, explain why we went open source and for this particular project, and look at the opportunities that gives. We went through a certain development process, so I'm going to try and explain that and see what opportunities that gives and what impact that gives, particularly to defense industry. So next slide, please. So everybody's heard of open source, but I do like to look back at the contrast that Eric Raymond made 22 years ago now. That's incredible. In his book, the contrast is between the cathedral and the bazaar. If there's one place where software is built like cathedrals, it's still built like cathedrals. It's in defense. The defense industry really prizes these sort of elegant, large software projects for the kind of aircraft carrier type software projects. And while there's no doubt which one of these looks the best, the cathedrals are elegant, but they're hugely costly to maintain, extremely laborious to upgrade or modify. In contrast, this is the contrast that Eric Raymond makes, the Bazaar approach, where you're releasing software early and often, you're delegating everything you can, gives you a lot of liveliness, a lot of vitality in your software, and the ability to upgrade very quickly. As you can see, in that Bazaar looks different every day that one visits it, because it's basically being upgraded to meet the needs of the customers. And I'd put one more analogy in here: private chapels. And in the signal processing industry, I think we are guilty of private, often MATLAB code libraries built with intricate care and jealously guarded by. And these, I think, perhaps are what Eric referred to when he talked individual wizards as well as small bands of. And I think the point of open source is that you can have all the advantages of your own code library, but many contributors from other like-minded individuals. So we used to look at open source for defense applications. So next slide, please. And that area was tracking and state estimation. Tracking and state estimation is critical for military situation awareness. Across almost all the domains of military, there are a large number of instances where we need to gain situational awareness of the combat environment. So we do that by various guises of tracking and state estimation. What do I mean by state estimation? I mean estimating the parameters that describe the state of any entity or group or event or situation, basically anything. This can be anything from the sentiment state of a population, or the area of contamination of a CBRN release, or the state of readiness of a terrorist cell, or the kinematic state or of one or a number of objects. So that last one, of course, is what we call tracking. So when I say tracking and state estimation, it's really just to emphasize, because tracking is state estimation, it's really just to emphasize that that we want to look beyond tracking as well as the standard tracking software. So next slide, please. So if there was a genie coming out of one of these lamps here, granting 3 wishes, I think the wishes might be from an academic researcher who would like to show the performance improvement of their tracking and state estimation algorithm without having to reproduce others' methods. And in the defense industry, that industry wishes they could use state-of-the-art approaches in the new product they're developing. And government laboratories wish that, at SSPD and other lesser conferences, they hear about so many new methods, and I wish I knew which of these actually works best in practice. And an open source approach that, as I'm about to describe, grants these wishes. So let's have a look at the open source approach for tracking and state estimation. So can I have the next slide, please? So this is Stone Soup. This is a project that we've been building. It's built on a framework made of Python, released to GitHub using SciPy. If you can just build this one, Maddie, that would be fantastic. I think there's 5 clicks here. What we plug into the framework are algorithms, yes, but also data and sensor models and simulators and metrics. In other words, there are a number of components there which are not just about the algorithms, they're about the evaluation of those algorithms, particularly the simulators and metrics, and we'll see some examples of those later on. So that's Stone Soup. The whole thing's built in Python, but one doesn't have to use Python if we can develop interfaces into your MATLAB code, for example. So next slide, please. So Stone Soup's key design principles are open source. Yes, we've talked about that. So what we want is members of the tracking and state estimation community to contribute in a very rich way. That's the idea of open source, but modular as well. The idea is that we have modular components that can be assembled and swapped in a predefined way. So you can swap a Kalman filter, for example, for a particle filter, and understand the difference that makes. And that gives you an interchangeable design principle, but not just the sort of large level components, interchangeable at the sub level as well. So you can swap, for example, transition models within your Kalman filter. And also well documented. The key to open source, I felt, was to have a very well documented code base, and that does 2 things. That encourages people to join in, but it also encourages people to make their contribution well documented as well, because it sets an example. And so it's worth the extra effort, I think, to document one's contributions. So next slide, please. We had a development process. I think the extreme open source community would talk about developing completely from scratch in the open, and we did consider that. But actually, what I felt was that we needed to build a bit of a model, a framework that was understood before we released it as beta. So we had a consortium phase where we were building as an alpha version, the framework and the basic principles of the Stone Soup software project in isolation, and then at beta we went open. And what this does is it cements the key design principles before we go open, and prototypes that class interface structure, which I'll tell you about in a minute, because otherwise it's very difficult to build up any critical mass as we go forward. It's very difficult to get people's momentum on an empty page. So you need to kind of show what it's supposed to do and show the point of it, but also to prototype that class interface structure. It doesn't mean to say it's unchangeable, but it gives some guidance to the community about how to build your component classes to dock into an existing interface structure. So to avoid complete amorphousness, we did a small consortium phase before we went to beta, and I think that has helped. It meant that at the beta release point, which was April 2019, we were able to say, look, this is the kind of thing we expect to be able to do with Stone Soup. So let's go forward and we can show what's in that, what was in that beta release. The next slide, please. So these are the sort of key top level classes that we put in the beta release of Stone Soup. So we're talking about readers, which are able to read from a data file or a data stream. So these are classes that are dedicated to that. Writers, which do the opposite, which write out the output, and then inside the body of the software, there are simulators which allow us to simulate if we don't have the real data, and then detectors which act like the actual sensor, and those feed data, detection data, into the main algorithm class, and then around the outside, this is on the left-hand side on the diagram with the green arrows. There are the ground truth comes down the outside and into a metric generator. So that metric generator is a key component for the evaluation, because not only do we want to run the algorithms, we want to be able to evaluate them. So that gives us that strand for the ground truth to come, and then that creates a set of metrics which are able to be written out to tell you how well that algorithm has done. So those are the key top level classes, and if you move forward one slide, we can drill into that algorithm box and see what's inside there. So here the classes are designed around a typical tracking algorithm. So typical tracking algorithms have a predictor and updater stage, and you can see that predictor stage right in the middle of the screen, and the updater on the right hand side, and they're buried within hypothesizer and associator classes, which allow that prediction to be part of a track hypothesis. So that the transition model, that's a replaceable component, so you can put in whatever transition model you like, goes through into the predictor stage, and then you can predict according to your transition model, and the measurement model goes into the updater stage, so you're able to see what the likelihood is from your measurement model when you go into the update stage, and so that's a typical version of a tracking algorithm. But of course, there are many different flavors of tracking algorithm, so you can put these things together in a different form. And of course, there are things like track before detect, or things like point process state estimation that would look slightly different. So this isn't sort of cast in stone as a template. This is just an example of how you would put together a tracking algorithm with those subcomponents. But the key is that once you've a reasonable template for your tracker, you can then start playing with the different different flavors of algorithm in these subclasses. You can change your predictor, you can change your deleter, and you can really understand what it is that drives the performance that you're seeing in your tracker. What is it that you've got the right transition model, or is it that your associator and hypothesizer is working better than it was? So, and in most of these sort of cathedral-built software projects, it's very difficult to actually take apart where that performance is coming from. So that's one of the key advantages that we saw from Stone Soup. If you could move on to the next stage, next frame, please. So another facet of Python which enables us to do this is the strong object orientation of Python. That enables us to do abstraction, so we can build these trackers as hierarchical objects. So, for example, a multi-target tracker may contain those components that I've just been talking about as part of the hierarchy, and then underneath your predictor, for example, there might be a hierarchy of predictors. And you can inherit a general property of a predictor or an updater as you go down that stack, and then that gives us that interchangeability. So we use the object-oriented approach to give us this interchangeability, and that's extremely rich. It means that even a non-expert can replace, for example, and this is the example in the diagram, a Kalman updater with a particle updater. Without really having to get into the maths and understand exactly what's happening. It's a line of software. It's a line in the Python rather than a mathematical operation to compare these two updaters. And so that's really the idea. If you remember back to the original 3 wishes, one of the wishes made from people that want to compare performance of these algorithms may be that they would like to do so without having to really get in and understand all the intricate maths of each of these methods. So next slide, please. So here are some of the algorithms available. Just like our stall in the Marrakesh Medina, there's a lot to choose from here. We've got predictors and updaters, so I'll call those filters in the Kalman filter family, the particle filter family. We've got some Gaussian mixture point process devices in there, and then there's a lot more one can play with. There's different associators. There's a big list, all the way from very, very naive nearest neighbor type association, all the way through to PDA and JPDA. We've got various flavors of deleters, hypothesizers. Initiators is a really interesting area of exploration because it's unsexy in the academic world. But it's critical for defense industry for those track initiations to occur at the right point. So that's something that one can play with, and you can really get an idea of the performance of a set of trackers by playing with these things and understanding what happens. And part of that picture is to look at the metrics. So there's a couple of metrics here, the OSPA and GOSPA family of metrics and some SIAP metrics. But of course, one can write metrics to suit your own particular needs. You can write metrics which favor particular behavior that you want to see and penalize behavior that you don't want to see. So you can use that metrics class in a very rich way rather than in an academic way. But of course these are just the standard set of algorithms available, and I would encourage users of Stone Soup to get in there and put in your particular innovations and put in your particular areas of research into these and enrich these classes of algorithms according to the direction that you would like to pursue. So this gives you a base, a code base that you can build upon, and reduces a lot of the effort it takes to before you've actually started your particular innovation. Next slide, please. And as part of, you remember, algorithms is only one of the 5 boxes. So here's an example of another one of the 5 boxes. That's the simulators available and the sensor set available. There's a large suite of different simulators that you can use to set up the kind of scenario that you want to study: single target, multi-target, single or multiple transition models, various different flavors of sensor, including bearing or range or elevation, and there's even a AESA radar in there with various beam patterns of radar. So you can really go to town and set up a scenario that tests your algorithm very in a challenging way. Next slide, please. So there's some examples of use now. I'm going to have to zip through some of these because we don't have a lot of time. So I might skip over this one a bit quickly. This is an example of fusion of radar and AIS data. This is just using a standard set of tracking algorithms, an unscented Kalman filter with some global nearest neighbor, with a Ornstein-Uhlenbeck transition model, and this enables us to explore the fusion of 2 different modalities. Here, this is in the west coast of Scotland, and we're looking at radar and AIS data of various shipping traffic around the west coast of Scotland. There's a link in there which enables you to open up a Chrome version of that map and zoom around, but we won't do that at the moment. Let's see if we can move on and get some time. Move on to another next slide. So this is looking at space surveillance. So here we're looking at the use of uncertainty in orbit track estimation. So that first diagram, the diagram on the left, shows what you get if you don't use uncertainty in when you're doing your orbit determination. You can see that it's quite error-prone track estimation of that particular space object. But if you use some uncertainty, and this is a particle filter type uncertainty, you get these diagrams on the right, and so you can see that uncertainty is actually a more accurate estimation of the uncertainty of your track. What we hope to do is to use the particle filter propagation and prediction parts of Stone Souk to propagate that along the track, so to see how that uncertainty grows. Next slide, please. So this is a video. I wonder if you would run the video, please, Maddie. So this is about maritime situational awareness. We're trying to set up an advanced scenario to study maritime situational awareness. I apologize. I think you can just click on. Yeah, that's it. Just click on that. So here we have a situation where we've got a ship, which is the dot in the middle, that's surrounded by two circles, and that ship is detecting, with a number of sensors, detecting a group of vessels, group of dhows, but there's a drug trafficker in there. So first of all, we're using ELINT, which is bearing only, and we're seeing that track actually is hugely erroneous and just drifting off. That's because you've only got a bearing on your track. So what's happening now is that the ship's helicopter is able to go off and visit a couple of vessels that have moved away, and then that's starting to create some a bit more certainty on the tracks of those two. Plus, there's an overhead sensor which is able to give a bit of an overhead image on the others. And so, as we bring this scenario is just exploring as you bring in sensors into a complex scenario, how that cuts down the uncertainty and makes that track more accurate. This is again a work in process, and it's got synthetic parameters to avoid classification restrictions, but it just gives you an idea of the kind of use that we're making of Stone Soup to set up advanced scenarios and really understand the level of performance you get in those scenarios. Next slide, please. Well, I won't run the video on this actually because we're running out of time a little bit. But here we've created an interface with Sapient. Sapient is an experimental multi-sensor fusion system, which is part of Dstl's work. So there you've got smart sensors at the edge doing some processing and pushing a process data into a maker. And so we're able to connect Stone Soup up to be a version of that decision maker, and then do some tracking on the messages, the Sapient compatible messages that we get from the kind of sensors you can see on the bottom of the screen. So actually, we've just got, if you did run the video, you've just got the target moving in a figure of 8. It's fairly simplistic. I just wanted to highlight that we're using Stone Soup to connect into sort of more external, more real systems, and effectively configure Stone Soup as the decision-making module in a Sapient system. Next one, please. So this is interesting. So this is connecting up a tensorflow object detector as the detector in Stone Soup. So this is a good example where you can create an inherited class, inherited subclass of that detector object, and then you can make that any kind of detector. So here, a TensorFlow deep learning detector. So you can see that the original videos on the left. In the middle, you've got some TensorFlow detections. Those the bounding boxes on the vehicles, and on the right-hand side, that's the tracker forming tracks from those detections. Now, that particular movement is not that challenging, or there's a little bit of a curve on it. But if you move on to the next slide and run the video on that, that's effectively because now we've set up that in Stone Soup. You can now run pretty much any video on that, as long as you have a TensorFlow trainer, a trained TensorFlow model. If you could run that video quickly, please, Maddie, that'd be fantastic. Then you can see actually we've got a TensorFlow object detector that's trained on people, and it's still using the same structure in Stone Soup. So now you've got those people. You've probably seen this kind of thing in every machine vision conference, but actually behind those people, there are trackers being run, and you can tell that if you look at the right-hand side, when the people disappear behind the hoarding, the track continues. So that indicates that there's predict stages carrying on from those tracks, and indeed there are. So that really helps. The problem that's shown here is that it's very, very difficult to keep track of objects. It's relatively easy due to the magic of machine learning to detect those objects, but to track them in this complex, obscure movement, you really need a tracker. And the machine vision community don't often use trackers behind their work. So this is a really good example. Fairly vanilla tracker parameters, a Kalman filter, constant acceleration model, but it just adds a lot of value into that kind of scenario. Next slide, please. I think I better zip through to the end now, as we're running out of time. So I'd love to run this video, but I feel that I don't have time. So this is just to say that we're doing some typhoon radar modeling, where we're looking at the air intercept between two aircraft, and running that as a stress test into Stone Soup. Next one, please. And this is the kind of impact we've got. We've got a large number of academic and industrial and government entities that are using Stone Soup, and also a number of different collaboration opportunities. For example, in ISIF, the International Society for Information Fusion, and in NATO, and in a group of government labs called TTCP. There's a large sort of body of collaboration around Stone Soup now. Next one, please. So very quickly, we've got a bunch of forthcoming additions as pull requests. So there's lots of different, you can see lots of different interesting algorithms in there. So these are algorithms that have been written, and we're awaiting review and incorporation into the Stone Soup base. Future direction is a lot more sophisticated algorithms to really get under the skin of some of those complex methods. But what we need, and this is an appeal, is a larger review community. So I would appeal to people that want to contribute to not only contribute but to help us in the review of things that are in the pipeline. Okay, I better move on to the next slide, please. So the implications for the community are that really this is a bit of a snake oil filter for algorithm claims. There's, in the academic literature, there are lots of algorithm claims about the performance of various algorithms, and what we need to be able to do is to understand which of those are true and generalizable across multiple challenges, and which of those are specific pockets of performance around a particular scenario that's been chosen. It also enables rapid prototyping. And one of the really good things that we're seeing is that we are enabling accelerated personal development. So this forms a suite of training material, and we've actually gone out into the Fusion conference and used this training material as part of the tutorials in the Fusion. It really helps to bring people up to speed in the basics of tracking and all the different types of views. Right, I will stop there because I have overrun, which I apologize for. So, are there any questions?
Paul, thank you. That was an excellent and truly inspiring talk for the first session of SSPD. We do have some questions. Maybe I could abuse my chair privilege to start off with and ask my question. What you seem to be saying at the end there is you'd like standardized data sets. Are you looking to try and sort of set up a league table of generic tasks and which algorithms are better in the same sort of way that the computer science community is doing in things like machine learning and image classification?
So I've thanks for that. That's a really good question, Mike. I have personally stepped one step back from league tables because I personally believe that it's very difficult to have a free lunch in this environment. It's very difficult to have an algorithm performance that is generalizable across multiple different scenarios. So the way I see it is that some algorithms are particularly good for particular challenges, and then they may fall down for other areas. So rather than an overall a league table which implies overall greatness across the whole of the suite of challenges, I'd like to see particular pockets of greatness showing up against particular challenges. So yes, absolutely. I really would like to have a large set of data and a sort of competitive nature within that data, but I think league tables for the whole tracking problem is a little bit simplistic, I suppose.
I understand. Okay, so we've got 4 questions. I'm gonna try and collapse them into 3 to to save time. So Ian Proudler and Richard Lane both ask basically on, so Ian asked about the open source community use GNU general public license. So what is the IP aspect of Stone Soup? And Richard Lane asks, can you submit code to Stone Soup using a copyleft software license so that it is only allowed for non-commercial use?
So we set up Stone Soup with the MIT license, which is a non-copyleft permissible license, and we allow submissions from under that license and a whole list of other licenses, including GNU, but copyleft is a bit of a problem for us. Well, not necessarily for us, but we perceive that to be a problem for the industrial community, and I would open that up to members of the defense industry as a question. I think copyleft is probably difficult, but do members of the industrial community agree? Because essentially it means that if you adopt that copyleft, if you adopt that code, then the whole of your code base becomes copyleft. Becomes sort of infected with the copyleft license.
Okay, so we got time for one more question. I'm going to merge two questions into one. So Matt Shaw from Thales says, how scalable is the framework in terms of volume and velocity of data? And Andrew McLean says, how do you approach testing? In particular, is there automated unit testing? So I guess really looking at the capabilities of the framework.
And I apologize, Mike. I caught the second part of that question, but not the first.
Okay, so how scalable is the framework from a velocity or volume of data perspective, and how do you approach automated testing?
Right. Yes. So in terms of scalable, so one of the things that we don't do in Stone Soup is worry about the actual time performance or computational performance of the algorithm. So we recognize that the Stone Soup framework is actually not the optimum that you would use if you were putting these algorithms into a product. So it's a evaluation framework rather than in terms of the accuracy of the performance rather than the timeliness of the performance, because the framework itself puts some impositions on the algorithm. So and that's going to affect the scalability. Although if it purely adds time, then that's an effect that we believe that we just have to cope with. If it causes the framework to crash because of memory, then yeah, that's something that we'd like to deal with. But I haven't seen those issues. I mean, that's partly about the performance of the computer that you're running it on. But so we believe that the framework shouldn't be the framework shouldn't be evaluating algorithms on their time performance. The second part of the question was about. Sorry, you have to remind me.
Automated testing.
So good. There is a set of automated testing called Circle CI, which is a set of tests that are performed on submission. So one runs a set of unit tests on the algorithms, and those are performed on submission of the algorithm. So yes, there is a quite a rich set of automated testing within the framework.
Perfect. Thank you once again, Paul, and hopefully that will inspire people to contact Paul, contact Dstl, and really engage in the open source Stone Soup project. Okay,
Thanks very much.